Chem 230. Chem 230, Fundamental Organic Chemistry, Glendale Community College in Glendale, Arizona with Dr. Bob Blake. And this first unit of the course, there are 4 units of the course. The first one is all to do with bonding and how atoms bond to each other to form molecules. And molecules, of course, form everything. So in our study of everything, we need to know a little bit about how things hook together to make other things. And so we're going to start off with a review, chapter 1 in our book, and the basics of what is matter made of. So the first little slide in the gap notes here, what I do is I read the sentence and see what I put in there, put in the blanks to make it make sense. So something is the smallest sample of an element that has the chemical properties of the element, and any professional chemist should tell you right away that atoms are the smallest samples of an element that have the chemical properties of the element. They used to think you couldn't break an atom, but we can break it. It really breaks it, and it stops having its properties if you break it. But you could take a sample of thousands of atoms of carbon and bring them to one atom of carbon, make them smaller and smaller until we get to one atom of carbon, and that's the smallest piece that will have the chemical properties of carbon. Atoms are composed of, and hopefully you've heard this before, but they have protons, neutrons, and electrons in them. So these are the smaller particles that an atom is composed of, and protons and neutrons live in the nucleus. The electrons live outside the nucleus. And here it's a little more challenging and ambiguous. Something has 6 protons, 7 neutrons, and blank, which I assume is the number of electrons, right? And if I'm talking about atoms, atoms are by their very nature neutral. So if you say neutral atom, you're being redundant. If something acquires a charge, it will be an ion. So when I think about atoms and how they're put together, 6 protons is very definitive. If an atom has 6 protons in it, it's element number 6. So element number 6, if you look on the periodic table, is carbon. So I can say a carbon atom, again, neutral carbon atom, has 6 protons, 7 neutrons, and since the 6 protons have 6 positive charges, in order for this to be neutral, it has to have 6 negative charges to cancel the charge, and that's where I would put 6 electrons in. So because atoms are electrically neutral, they have to have the same number of negatively charged electrons as they do positively charged protons. So I know this now makes sense. A carbon atom has 6 protons, 7 neutrons, and 6 electrons. The atomic number, Z, identifies the element and gives its number of protons. And this is something we alluded to a minute ago, that if something has 6 protons, it's element number 6 and has to be carbon. So the atomic number, Z, the number of protons, identifies the element. And that's a really key feature that we're going to work with later, is if you know something has 6 protons, it has to be a carbon. If it has 8 protons, it has to be an oxygen. 10 protons, it has to be a neon. And if you're familiar with the periodic table, the atomic number is the number of protons and identifies the element. The next sort of indicating number here, which is really important, is called the mass number. The mass number is not found on the periodic table. The mass number is the integer sum of the number of protons and neutrons that are found in the nucleus. So those are the particles that contribute to the mass of the atom, the protons and neutrons. Electrons are so light they sort of don't matter in terms of mass, although they do have mass. So in this example above, 6 protons and 7 neutrons makes a mass number of 13. So a carbon 13 atom would be more specific here, that the mass number is 13 because it has 13 nucleons, or 13 particles in the nucleus. The important point, we're not going to spend too much time in a fundamental course, but if you go on to a physical chemistry course, they will tell you very specifically that electrons are not best seen as particles, and in an atom especially, they act as waves and are very difficult to understand. So this slide tells you a little bit about atoms. They're made of protons, neutrons, and electrons. And the number of particles in the atom will be very important in determining its identity and its properties. So, good little introduction to building blocks that you build the universe with if you have that capacity. And here's a little reading assignment. So it's a good idea to read the book. And there's a little introduction in chapter 1. Then they talk about the structure of an atom, electrons in an atom, and then how ionic and covalent bonds are formed. And again, this first unit of the course, bonding is going to be the topic. So very interested in how things form bonds. And we're going to continue a little bit talking about atoms and the structure of the atom. So a little more information about mass of the atom. So the mass number, A, is its little symbol, is not something that's found on the periodic table. The mass number on the periodic table is actually called average atomic mass, not mass number. So the average atomic mass, and that's the average mass of the atoms of a particular element. It's a weighted average and it's a little more complex. So the thing on the periodic table is an average mass. The thing we're talking about now is the mass number. So the average atomic mass or simply called atomic mass by most people, the average atomic mass is found on the periodic table and is the average of the masses of the stable isotopes of an element. The isotope bromine 80 does not exist. If you look on the periodic table, you'll see that the atomic mass or average atomic mass of bromine is 79.9, so you might think bromine 80 makes sense, but it doesn't. Bromine, the element, is composed of almost equal numbers of bromine 79 and bromine 81. So if you have something that's 79 atomic mass units and something that's 81, if you have equal mixtures, then you'll get an average mass of 80, even though there's no particles in there that are 80 atomic mass units or 80 grams per mole. So really important to get the distinction between the mass number and a mass of a particular isotope versus the average atomic mass for the element. So one of my favorite little exercises here, and it's a good problem for exams and quizzes, is a little summary of the things that go into the subatomic particles and atomic composition. So we have an element symbol here, and this is the fully dressed up atomic symbol with the element symbol chlorine, Cl, that identifies it on the periodic table. The mass number A goes up here. The atomic number is almost never written in atomic symbols because if you know it's chlorine, it has to be atomic number 17. So that's something that's sort of redundant to write both, but if you want to be really complete and want to put the atomic number of chlorine down, you'll put it in the lower left here. And then this up here is the charge. So in an abstract way, we have the element symbol, X. So I like to use big old X to say whatever the symbol is that we put in there. And then the mass number is A, and that goes up here in the symbol. The atomic number Z identifies the element and is the number of protons and goes down here. And then over here is where we put the charge, Q. So Q is charge if it's an ion. If it's neutral, we won't write anything there. So for atoms, there'll be nothing written here. For ions, the charge will be explicit because it's important. So there's a charge. The A here, and I'm going to have a lot of arrows pointing at things, is the mass number. And it's always bugged me when I see the A, I want to say something that starts with A, but A means mass number. The Z, and I get the funky European Z there, is the atomic number. And that identifies the element. So some of the things that are true here, let me get that on the screen. The atomic number Z, mass number A, charge Q. And if we're trying to keep track of what particle we're talking about and what it's composed of, there's some very important truths to keep track of. So Z is the atomic number equals the number of protons and identifies the element. And where that comes into play here is for chlorine. It's written here that it's element 17, but we could just look on the periodic table and see that chlorine is element 17. The reason that it's chlorine is also in a more physical and fundamental sense because it has 17 protons, and that defines what the element is. So because it says chlorine, I know atomic number is 17, and the number of protons is 17, so sort of those three features are linked to each other through this relationship. Now we defined mass number as the number of protons plus the number of neutrons. And where that lives in the symbol is up here. Chlorine 37 means its mass number is 37. Now, if I know the mass number is the number of protons plus the number of neutrons, then I have super simple math here, that 37 equals 17 plus something. So this is the kind of algebra you give to first graders. What do you put in the box? 37 equals 17 plus what? And since these are two digits, maybe third graders, but 17 plus 20, ta-da, will make 37. So this clearly has 20 neutrons for it to be chlorine 37, because then the number of protons plus the number of neutrons equals the mass number. So this is a really important relationship and allows us to use the simple algebra to get, if we have two of these three quantities, the mass number, the number of protons, and the number of neutrons, we can get the other one. And the third, and sometimes the most confusing one, is charge, where again the charge comes from the balance of the protons and the neutrons. So like here, it shows a very odd chlorine 2+. Now the way chlorine got to be 2+ is it lost 2 electrons. So the number of electrons isn't fixed for a certain element. You can take electrons or add electrons in, and so chlorine with a 2+ charge means it lost 2 electrons. Now if it were neutral, chlorine would have 17 electrons, so the number of electrons and number of protons would be equal. If this was a chlorine atom, 17 electrons. In order to get +2 charge, it lost 2 electrons, so now it has 2 more positive charges than negative charges, hence the 2+. So the physics and understanding what's going on here is really important. And if we go ahead then and say charge, if we want this to mathematically work out, you're going to have a plus charge for every proton, so you add up the number of protons, and a negative charge for every electron, so you subtract off the number of electrons, and number of protons minus number of electrons will give you the right sign and the right magnitude on the charge. So this one, 17 minus 15 is +2. And this is a very peculiar chlorine, because usually chlorine gains electrons and forms chloride, but some maniac has knocked 2 electrons off of this chlorine, making a chlorine 2+. What's typically more stable, and I'll give you another isotope of chlorine, chlorine 35 is very common, but it's most likely going to be chloride Cl-. So it takes on a negative charge. For it to be chlorine, it has to have atomic number 17 and 17 protons. Now if its mass number is 35, 17 plus what equals 35, and if you just go by comparison, to have a mass number 2 lower, it's going to have 2 fewer neutrons. So 18 neutrons plus 17 protons makes 35. Check, mass number looks like it works out with these guys. For chlorine, it has to be 17 protons. Mass number 35 means it has to have 18 neutrons. Then in this one, since we have a negative charge, we have more electrons than protons for an excess negative charge, and it's only one more. So we have 18 electrons here. So now if we go 17 protons minus 18 electrons, we get the -1 charge. So here's a couple of examples of ions. One that's a little less stable, the chlorine 2+. One that's a little more stable, the chlorine minus. And how many protons, neutrons, and electrons would make sense given the mass number, the charge, and of course the atomic number I would normally go unwritten, but just for completeness I'm going to write in here chlorine has atomic number 17. Ta-da! So this is a great thing. We're going to have probably a little video on a table like this where we have 3 or 4 examples. We're given the number of electrons, neutrons, or protons. We can figure out what the symbol is and what the heck we're talking about, whether it's an atom or ion. So I hope that this is informative, some basic information on what subatomic particles exist, atomic number, mass number, and how it all fits together.